But in order to make, and the way in C++ works is that you put the template statement. So the template uses class object. Right before the function itself, you're defining the template. So you're calling my stack from main, which is a stack of strings. But then when you hit the print, you make the print call, is basically the template is going to see object as a strings. If you don't have that template statement at the beginning of the function, then it will not work out. Probably will give you a compiler error saying that, oh, the type match is not correct. Okay, so we put a template. Now my stack is a stack of objects, is a stack of a string. Now you're creating a temporary stack, and then you say a stack of object, temp stack, and then you say temp stack is equal to my stack. Basically, what you have coming, you're creating a temporary stack, and you're assigning it, yes, your temporary stack based on the data coming as my stack. And then you walk through the temporary stack. You see, loop through, while it's not, stack is not empty, then you're printing. So what is the true about the stack? Stack has got one pointer, right? And that's top pointer. And then you walk through the stack. You look at it, you take the top, you look at see what the top is, and then do pop. Pop does the top of a stack. Okay. So this is very simple. It's a stack. And I will ask you to provide how the reverse is going to work. What is the reverse of this my stack? So the top of a stack, so the top of a stack is jumped. You push THE, you push quick, you push prawn, you push fox, you push jumped. So jumped is going to be the top of the stack. Okay, and if you're writing a function called reverse stack, what happens? You just create a new stack and pop does the top of stack. The top of the stack is jumped. You push that onto the stack, onto the reverse stack. So if you do that reverse, then you can walk through print elements of reverse stack, and that should be the reverse of what you. Pop my stack and then push it onto reverse stack. And then call print with my stack. Now set my stack to be reverse stack and then call print, the same function. And, okay, so it's not that hard, right? Okay, so we learned. So the important thing is that you see at the beginning, you have to define things, template. You see, you're at the beginning of the program, you're defining all your, all your functions. but then you also say that those functions are going to use a template class object. Whatever you say as a class object, as a template, that's how the function has to accept. Once again, your strings are going to be mapped to object class because you said the template. Two functions, print and reverse stack. So let's talk about queues. Queue, the same idea here. But one thing I want to say, what is that using namespace std? You remember I told you in C++ is a multiple inheritance of objects? In Java, you only have single inheritance of object. You have multiple implementation of interfaces. But in C++, you have multiple inheritance of objects. So what happens is that you may have many objects that implementing the same methods or function signature, but the actual implementation are different. The signature meaning the function name, the parameters, and the return type of the functions are all the same between, say, object class 1, class 2, class 3. They all have function 1 with the signature exactly the same. But the implementation for each one is different. They do different, the goal is different thing. But when you compile your C++ code and then you do link, the linker is going to pick up, it's going to pick up one implementation because it's the same exact signature. So you don't know through that linking at link time which one is going to get. Okay, and so you may get the wrong one. It's compiled because it's a signature. Say you intend to get function 1 from class 2 or object 2, but they picked up the function 1 from object 1, class 1. So you compile a UMON, and then somehow in testing or customer gets the code, and then they say, oh, I'm not getting what I'm supposed to get. Then you have to reverse the, debug the issue to find out what's causing, So it's called the diamond problem. The way to get around that is in C++, they have namespaces. And this is one of the namespaces is called std. What this says is that using namespace std. So when you compile this code, it says that, the libraries is just a world of umbrellas. One umbrella is called std, another umbrella is called Mausen, another umbrella called, XYZ, and so on. And then these guys, the objects are with the same signature are implemented under these umbrellas or namespaces. So when you say namespace std, it says that if there is an implementation for functions in this file, go and only look for std namespace, umbrella under std. Don't bother to go into umbrella XYZ, which may have the same method or function signature implementation. So with the namespaces, it reduces the problem with the diamond problem. I'm not sure it's fully guaranteed to get that totally is resolved, but definitely it's not going to go pick up umbrella 1 and 2 and then 10, and because once it finds it under one umbrella, it's going to say, oh, okay, I found it. I'm going to link the object. But when you say STD, it says, oh, I'm going to only look under umbrella STD. And if I find implementation for the functions, I'm going to use that. The reason I say that it reduces the diamond problem is because you could possibly, the STD is just one of the namespaces. For large applications, you will need many different namespaces identified. It is possible that, say, namespace XYZ, someone implemented a function with two parameters and a return type, an integer. And then say 6 months later, a year later, another engineer was hired, doesn't know. For large applications, it's very hard to see what you have. He's going to go ahead and implement, it doesn't happen with STD, but I'm considering you have many namespaces. You're using many umbrellas, libraries. It is possible that the engineer would not know exactly, so he's going to go ahead and implement again. Because under every namespace, there are modules. There's a large set of modules. Who knows what's going on in every module under a specific umbrella or namespace. So it's possible that you will have duplication of the same signature with a different intent. That means the goal was to do, the result to be on one instance to be something, on another thing, something else, but the signature is the same. So in that case, the linker is going to pick up the first one that it sees, and it may be a wrong one. It's going to see one, it's going to compile to it, link to it. Okay, namespace. So we have queue. Once again, we want to do a print queue function and then high priority queue. High priority. And so we put the template. We're going to say that my queue should be mapped to class object. Object, whatever is coming as a remember queue, generic object. With the template, you're mapping the generic to whatever is coming in. Okay, so you have print queue. Once again, at the beginning of every implementation, you're defining all the functions. In this case, we have two functions. Okay, so we have our main. And what we're doing is that we declare queue variable. We have my queue, which is a queue. If you look at the library in the include file, is a queue included, right? And then you have queue integer. In this case, we have an integer. So now you see, is the queue. Normally, if you used to a queue, so a stack has one pointer top, but queue has two pointers, the front pointer and back pointer, head and tail, front and last. Those are different and mean the same thing, okay? But you see, normally you say for operations of stack, you say push and pop. And for operations of queue, you say in queue or dequeue, insert, remove, delete. But in this case, you see, is a queue which has two pointers, front and back, but the functions of the queue library is using push. When you see that, you think, oh, is this a stack? But it's just as long as you know what you're doing with the, with the function, you can call it anything you want. But push here is a push into a queue. So what we have, my queue is push 26, 17, 86, 90, and 15. Okay. Now what you have is so we're going to do, now we're going to print queue. Okay, we're going to print queue. Look at what's going on in here when you declare, and this was true with the stack too, and the previous stack code. When you say queue in a generic int, my queue, you don't do any memory allocation yourself. The operating system is going to give you allocation for queue. That means you're not worried, you don't have to worry about managing the memory allocation. It is allocated by operating system by default, and then is taken care of by the operating system by default. So you don't need to have to worry about that. Okay, so we push in this case means insert or enqueue into the queue. And then we're printing queue. Then we do, I talked to you about high priorities. Okay. So high priority 30, high priority 85, high priority 77. The typecast here is that in typecast integer means that you wants to make sure that 77 is integer. It looks integer, but when you typecast it like that, it makes sure that it is an integer. Typecasting it into an integer. Okay, so print queue. We're going to walk through this. So we have our template at the beginning. So what is the generic is an integer. But so we are mapping the object class object to an int. So we're creating a temporary queue, temp item, and then we walk through the queue, and now you see the queue has a front function. What are we doing is that front means that you're taking so you're removing from the queue. So you have to manage, you call front. That means the front, it manages the front pointer. Because you're taking things out of the queue. So so I said that queue has 2 pointers, front and back, head and tail. If you're removing something from the queue, you manage the front pointer. If you're inserting into the queue, you manage the back pointer or tail pointer. This kind of things you shouldn't have studied in your algorithms class. I don't know if you had it with me or not, but so we are going to manage the front pointer. We have our queue has a front function. We're taking something out, assigning it to temp item, and then you're printing temp item. Then you pop temp queue. One thing to, when you call the front function, it's just going to take an item that's pointed by the first pointer. The management, so when you removing it, then you have to normally decrement the front pointer. But what happens in this implementation, you're making a call to the front function that takes the item off the queue and assigning it to temp item. But the actual pointer that is pointing has not been managed yet. It gets managed when you do a pop. The front pointer, this is a front function. The front pointer is going to be managed by the pop function. See, you take the item out and then you manage the pointer by pop function. Okay, so you do that in high priority. So let me talk to you about what happens with the, you probably studied this in your algorithm class again. I'm going to review it and also show the C++ implementation for it. I want to take you to this thing. So what we have this is a queue. With the C++ implementation, you have a method push, insert, and pop from another end, front pointer. You have 2 pointers, front and back, and functions pop and push. It's storing data into the priority queue. Okay? It's storing data into the priority queue. The data structure is based on heaps. The data structure is that if you have a minimum heap data structure or maximum heap, if you're using is a minimum heap, the value of the parent node is less than or equal to the value of the child nodes. So the parent is smaller than the children. So for priority queue, you using either minimum heap data structure or maximum heap data structure. So if you're using min heap, parent is less than the children. If you're using maximum heap, the parent is larger than the children. Look at this implementation, printing all elements of priority queue. So what happens? We have a priority queue. You see the data structure. It is in the include queue, and then the priority queue, and the genetic integer. Okay, so we are looking at this code here. And we see, what are we doing? We have a priority queue data structure with the genetic integer, and the variable is prior under queue. And then we do the push those integers into our priority queue. And then we walk through the priority queue. As long as it's empty, we're going to print what the top is. And then we're going to pop the top, removes from the top. And so we're going to, yes, we're going to print the top, and then we're going to do the pop, and then the loop is going to take the next top, next top, next top, next top. So by default, when you're using this priority queue data structure, okay, it uses that you're using a maximum heap. What is maximum heap data structure? The value of parent is greater than equal to the value of child node. So maximum heap is the parent is larger than children. So what we do, look, you look at your, when you do push those integers, you push 10, 30, 6, 259, and 7. But look at the output. The output, because you did it uses the maximum heap data structure for priority queue. The default is the max heap. So you see, when you do printing, it's going to take the highest one first, the next one 15, the next one 10, the next one 9, the next one 6, and the next one is 2. Okay. And these are the functions that are supported within the priority queue: size, empty, push, pop, swap, in place. I'm going to send you this link. You see this code? It says that it does the minimum heap, but it really doesn't, because this code is exactly the same as this. So, but this code is it uses maximum heap data structure for the priority queue. So is this one. So the report output is wrong for this program. It's exactly the same as the first one. Okay. But I'll show you. And the result here is really saying that we're using minimum heap. Our priority queue uses minimum heap data structure. That means the parent is smaller than its children. When you push, so let me show you this implementation here. Okay. So this is okay. So we have a priority queue. Okay, priority queue data structure is like the same as what I just showed you. And then we go. So what is this? What do you think this should print? This should print maximum heap. This uses maximum heap data structure. That means the parent is larger than children. So you push in those elements. The result is, you see, is the parent 30, 20, 10, 5, and 1. Okay, so let's see how we're going to do use the minimum heap. That is, our priority queue uses minimum heap data structure. So you see at the, okay, so you have a show priority queue function, returns void. And then we have main, so we are declaring our a variable name so our priority queue is got int, a vector, generic int, and then greater function int. Or I'm sorry, greater variable int. And you see that is so the name of the variable is gquiz. Gquiz is priority queue with those signatures. Don't read that as a greater than this, okay? That's just the end of the parameterized for priority queue. It's just it puts in a space, makes it to wonder why. Our variable is just this, declaring a variable to be priority queue with those signature. Okay, 3 elements. So we're going to push into this, our priority queue, and 10, 30, 20, okay, all of that. So, and then we're going to call the show priority queue, pass our priority queue to this function. Priority queue is this function that we, okay, so we are gquiz is really GQ, right? The rest of it is just parameterized. Show priority queue only has one parameter, and that's GQ, but the type of GQ is all of those priority queue with 3 parameters. With 3 genetics. Show priority queue has 1 parameter. Priority queue has 3 genetics: int, vector of int, and then greater int. Okay, inside show priority queue, we're going to do priority queue int, vector int, greater than int, g equal to q, gq. Okay, and then we walk through our, okay, so we are going to declare, we're going to declare a variable called g of type priority queue, and we assign to it GQ. And then now we're going to go walk through this G, which is a priority queue. If as long as it's not empty, we're going to print the top, and then we're going to do pop. We loop through, and then we adding a new line. /n means new line. So show priority queue, and then we say the queue size, the queue type, and then we're printing pop quiz, it could pop and show queue side. So what do we expect here with this? This is going to be is implementation of the priority queue using minimum heap data structure. So we expect that the result is going to be slow from small to large. You see, in this case, is 1, 5, 10, 20, 30. Okay? And the reason for that is because of this signature priority queue with the graded. So internally, it's going to do all those evaluation and that actually happens when you do the push. You know, with the push that you're doing it on the G quiz of type priority queue. That push implementation manages this minimum heap data structure. You send G quiz dot push and then the value. You do show priority queue and G quiz pop and so on. So the rest is simpler. But you see, to get a minimum heap data structure implemented, you need to have priority queue parameterized or genetics with those three things: int, vector of int, and then graded int. Okay, so you learned a stack, you learned template, you learned queue, and you learned priority queue under C++. So that's great. Let me take you to another topic. What's going to happen next? So we talked about shared memory as one form of IPC, inter-process communication, and then message queue as another type. So today I talked to you how to build, how to have processes communicate through sockets. Okay. You have a client process and wants to talk to a server process. And the communication between this client and socket and the server uses TCP/IP. TCP/IP protocol. So you have clients and you have a server. If you notice quickly, you see that, so obviously is an IPC, socket communication in IPC form of socket communication. So that means you need to provide a set of system calls. Okay, so you need to provide system calls. The client and the names that you see here, you know, on the client side, you mainly need to provide three system calls. One is the socket, the other one is connect, the other one is send and receive. 4 actually, send and receive 4. On the server side, this number of system calls is a socket, set socket option, bind, listen, accept, and then send and receive. What happens is that you bring up the server. The client cannot communicate to anything that is not up and running. So first you bring up the server side. In this diagram here, server starts first. And then client tries to connect and creates a socket, tries to connect to the server. And then you see on the server side, you see is a listen. What that means is that the client is going to get blocked on the listen. I think you know. I think you know what blocking is. So when you do communication, so either have multi-process communication or multi-threaded communication within each process, but between processes, if in a general definition, you get blocked if the resource that you're trying to access is already taken, and you're trying to access too, but it says, oh, it's already taken. It has a lock on it. So you get blocked. If the resource that you're trying to access already has a lock, you're going to get blocked. And when the process finishes the use of the resource, it's going to do unlock. When it does the unlock, it unblocks you. Okay? Block, blocked, unlock, unblocked. Because two hands cannot go into the same resource. So what happens is that, but the context here is a little different, but the same idea. Still, the client gets blocked on the listen. So you created a socket, you set the options for the socket, and then you do a bind. But what bind is a system call that it will take your address. A socket is an address and a port. And you know, soon I will show you when you do socket communication, you have to use some specific family of interfamily. One of them, for example, is IF_INET. That family uses an address and a port. Another type of family is the IF_UNIX. I'll show you that, okay? That is, it uses a path. You have to provide the path name to. And so in a general sense, every computer has an address. Your address is unique, my address is unique, everybody's address is unique. And all of us and our computers have port numbers. A set of ports available. Okay, so when you say you want to do socket communication, then you have to provide what family of internet family you want to use. If you use the IF, it's called Internet Family _INET, that means that you're going to use the address space under IF_INET. So when you create a socket on the server side, you create a socket, then you set this option, socket option. Then you do bind. You're binding your address to that family of addresses. Okay, now The next thing is the listen on the server side is listening. So listening, it says it's waiting for a client to try to connect. So when a listen happens, the server gets blocked until the client attempts to connect to the server side. So what is the block means is that you're sitting there, it's not going to make any progress on the server side. It's not going to go on called accept system call. It's going to sit on the listen. That means it gets blocked until an attempt is made from the client to connect to the server side. You see? Once an attempt is made from the client, then the block is removed. Then if listen is going to fall through and execute accept. Once, if accept is successful, then the client and server are connected at this point. And now they can send and receive messages to each other, you see, back and forth. Okay, so a few things. So you need to, I talked to you about, so you have a socket file descriptor. You know, every time you open a file, open a device, or open a port, you returns to you a file descriptor. And then you use file descriptor to basically read, write, send and receive, you know. But in here, we're doing a socket file descriptor. It's a file handler. The socket is treated as a file. Use the socket FD file descriptor to do various operations. And then you see the domain is an integer communication domain, like as I mentioned, AF, address family, INET. And I talked to you, you know, IP version 4 protocol, address family, INET 6, IP, address family, IP version 6 protocol. The difference between IP version 4 and 6 is just with the, because you see everything is based on computers. Everybody's sitting at home communicating to the world. So that means we need more addresses for so we can support more computers. With the IP version 4, we basically saturated the world. And IP, you know, IP version 4 is that you see, you say 127.1.1.1. That's just the local host, right? That's an IP for, but that's the format for IP version 4 protocol. Okay, so we needed more addresses than just, you know, the address space that it's provided with the version 4. That's why version 6 was developed. And I take you through this here, okay? So this thing, you know, I will have you to read this, but mainly, so how do, let me actually, IP4, you see the IP4 version 4,